For this problem, there is NO, nitrogen oxide, and O2 gas separated in different compartments, and the reaction will be initiated when the valve is open, but you can see the conditions of each gas as described in the problem. The first thing that you want to do is calculate the moles of NO and O2 using this information and the ideal gas law, PV equals nRT. So the moles of NO will be equal to the pressure, which is 360 torr. We must convert that to atmosphere. The volume is 4.0 liters, R, the gas constant, 0.0821 liter atmosphere per mole Kelvin, and the temperature of the whole system is 25 degrees C, which is 298 Kelvin. So if you set this up, you'll see that all the appropriate units will cancel except for moles, so atmosphere cancels, liters will cancel, Kelvin will cancel, and torr will cancel, leaving you with 0.07744 moles of NO in this compartment. The number of moles of O2 in the compartment, calculated in a similar way but given different conditions, you've got 0.996 atmosphere times the 2 liters, divided by the gas constant times divided by the temperature, 298 Kelvin, giving you 0.08142 moles of O2 in the compartment. Now the valve is opened, these two different gases are allowed to react. So what you should recognize at this point, this is a limiting reagent problem because the amounts of both reactants are given. So you must determine the limiting reagent by determining the moles of, NO2 produced. And this is done by considering each of the reactants as a limiting reagent. This is one approach. So if we take this approach, if we assume that the nitrogen oxide is the limiting reagent, the moles of NO2 produced based on the stoichiometry, that there's 1 mole of NO for every 1 mole of 1 mole of NO2 for every 1 mole of NO, you'll produce the same number of moles of NO2 as the amount of NO that you produced. If, however, the oxygen gas were limiting reagent, the number of moles of O2 generated times this molar ratio is 2 moles of NO2 for every 1 mole of O2. That would produce 0.1628 moles of NO2. So if you take this approach, the limiting reagent will be the nitrogen oxide, since the moles of NO2 produced is less than the moles of NO2 produced if the O2 were assumed as the limiting reagent. So at this point, our overall goal in this problem is to figure out the total pressure. Because nitrogen oxide is the limiting reagent, there is no NO left at the end of this reaction. Therefore, the pressure exerted by NO is 0 at the end of this reaction. So we must focus on the partial pressures of O2 and the partial pressure of NO2, which is the product, to account for the total pressure once the valve is open and the reaction is complete. So the pressure of partial pressure of NO is equal to the number of moles of NO2 produced, which we've already calculated, times R, T, divided by the total volume. And the assumption that must be made is that when you open up the valve, you can just simply take the sum of the two volumes of each compartment, which would be 6 liters. So if you do that, you'll see that the liters will cancel, Kelvin will cancel, moles cancel, leaving you with atmosphere. And the partial pressure of NO2 is 0.3158 atmosphere. Now we've got the partial pressure of NO2. So now our goal is to figure out the partial pressure of O2. To do this, we have to consider the amount of the amount of O2 that remains at the end of the reaction. To do this, we have to take the difference between the initial moles of O2 and the moles of O2 consumed. So the number of moles of O2 consumed will simply be the moles, we're going to relate the limiting reagent to O2. The moles of NO that react, given the stoichiometric relationship between O2 and NO, that tells us that 0.03872 moles of O2 are consumed. So we take the difference between the initial moles of O2, and the amount of moles of O2 consumed, and you'll get 0.0427 moles of O2 that will be remaining at the end of the reaction. This is what gives rise to the partial pressure of O2. So we take the, let's go back to our previous slide here. We're going to take this information and plug it in to our ideal gas law to figure out the partial pressure of O2. In doing so, we'll figure out that the partial pressure due to O2 is 0.174 atmosphere. So we plug that in here, and then we have the partial pressure of NO that we calculated. The sum of the two is going to give us our total pressure.